Hello everyone, welcome to 3 Minutes Engineering Concepts. The idea of this website is to explain any engineering concept in 3 minutes, and we will be able to explain any advanced or fundamental concept in mechanical engineering and material science. If you like the idea and if you like the videos, then please like, share and subscribe to get the regular updates, and also if others can benefit from it as well. Okay. Before jumping into the details of FE analysis and FEM method and its theory, which gets really messy, then I thought that I should give you a brief overview or revisit of what really is involved in mechanics of solids. Most of the time, to understand the FEM concepts, I will be concentrating more on truss members because this is the simplest of all the elements in solid mechanics. It's a 1D structure. So in this video, I'm going to explain to you what are the fundamental equations involved in describing the behavior of a truss element. So if you look at any typical structure like shown in the figure here on the right hand side, then this is a typical truss structure. And so this is your truss structure in this case, and this one here, and each truss member in this truss structure is a truss element, and it's a solid which has one dimension which is much larger than other two dimensions. And if we apply a force in one direction as shown in this diagram here, then it will create a uniaxial deformation in x direction. See, since I'm denoting this as x direction, which is the longitudinal direction of the member, and that's why sometimes it's also termed as a 1D solid. In this slide, I have shown you a truss member which has x as the longitudinal direction as shown here, and then I have a force Fx acting in x direction. This force Fx will cause an end displacement which is denoted as u in the bold letters. U is a vector quantity which can have in reality three components, x, y and z, and you can also have rotation in three-dimensional objects. In this case, since we are working with trusses, so we only assume that the main deformation is only in x direction, so my u will have only one component, that's u, or ux I will call in this way. Similarly, based on this, I can relate my u, which is a displacement, with the strains, and also I can relate my strain with the stresses. So that's the main thing. Now we need to find out how we can define these. And so we need to find a relationship for sigma x, which is the stress in x direction due to this force, and also the strain, which is caused by the stress or this force in x direction. So for any small element or infinitesimal element of the truss, going back to the basic solid mechanics, I can describe or link the strain in x direction with the displacement is as given by this equation here, and which is nothing else but the variation of u with respect to x. In three-dimensional space, it will be a function of y and z as well, and u will become u, v and w, for example, in that direction. So the equation which relates the strain with the displacements or deflections is called the kinematic equation. So since now we know the relationship between the strain in x direction and the displacements using kinematic equation, the next step is how to find out or compute the stresses in x direction. So to compute the stresses, the fundamental relationship which you always come across is called Hooke's law, which is nothing else but the stress is directly proportional to strain in the elastic regime. And when you remove the proportionality sign, you replace with a constant in simple terms, and that is shown in the first equation here, which clearly shows that E is the Young's modulus, and that's my proportionality constant. So now this equation, which comes from the 1D Hooke's law, is my constitutive equation which relates my strains with the stresses. So indirectly I have linked my stress with displacements if I use both constitutive equation and the kinematic equation which I showed you in the previous slide. Using the dynamic equilibrium, that is, if I say that a force is causing some kind of displacement in my body, and obviously this force is changing with time, then my overall dynamic equilibrium equation will be sum of all forces equals to 0, and that is given by here. So I have applied force Fx, which will cause some acceleration in the body, which is rho u double dot, and will also cause stresses, and that force due to the stresses is given by this equation, which is partial derivative of sigma x with respect to x in this case, which is a 1D case. If it's a 3D case, again you can imagine how complicated equation will be, or will be a set of equation in that case. So now what I do, I just substitute the values of the constitutive equation in this equation here, and I replace my sigma x with the constitutive equation, which is E epsilon x, and then I also replace my E epsilon x with the kinematic relation which was shown previously, and I ultimately get a relationship which is in terms of displacements and forces. So now I have overall dynamic equilibrium equation for my truss element in 1D. If it's a static problem, this means my truss is fixed from one end and it can only have deflections or displacements, then I can replace this inertia term, which is this part of this equation, and I will get the static equilibrium equation given by this simple equation. You can solve this differential equation analytically because it's a 1D case, and you can find out how the deflection is related to force and the coordinate system, and I will show you later on how you can find that in a solved problem. But in reality, when you have many truss elements, it becomes very difficult to solve it analytically for each of the cases, and for that cases you will try to solve this equation using different types of approaches, and one of them is called finite element methods, which will be now explained in next lecture. Thank you very much for watching, and I will see you in the next lecture.